Hi guys, welcome to our first video lecture. This lecture is entitled Orthogonal Functions. What the heck are they? We start by defining orthogonality in the traditional sense. Etymologically, the word comes from the Greek orthos, which means upright, and gonia, meaning angle. If we translate these Greek words to Latin words, we get rectus and angulus, which is where our word for rectangle comes from. Most commonly, when we talk about orthogonality, we're referring to vectors. Two vectors are orthogonal, you mean that they're perpendicular. Here we have our three unit vectors, which form the basis of three-dimensional Euclidean space. Each one of these vectors, I, J, K, forms a 90-degree angle with each of the others. These three vectors are therefore orthogonal. Given any two vectors, say u and v, how can we test to see if they're orthogonal or not? We can define an inner product, acting on u and v, as the sums of the multiplication of the components of the vectors. Based on this definition, the vectors u and v are orthogonal or perpendicular if and only if their inner product is equal to 0. The inner product, defined in this way, has the following properties. The inner product of u and v is equal to the inner product of v and u. If you multiply the vector u by some constant c, the inner product of cu and v is equal to c times the inner product of u and v. The inner product of a vector u with itself is equal to 0 if and only if that vector itself is uniformly equal to 0. Otherwise, the inner product of a vector with itself is always greater than 0. And finally, the inner product of a vector u plus another w with v is equal to the inner product of u and v plus the inner product of w and v. In this lecture, we will define a concept of orthogonality for functions. How do we define this concept? There's no obvious or geometrical meaning of two functions being orthogonal. We define the orthogonality of vectors mathematically in terms of an inner product. If we define an inner product of functions satisfying the same conditions, we can define two functions as orthogonal if their inner product is 0. With that in mind, we define the inner product of two functions f and g over an interval from a to b as the integral over that interval of the two functions multiplied together. We can then say that f and g are orthogonal if the inner product is equal to 0. In this example, we're going to show that this set of functions is orthogonal on the interval from negative p to p for some real number p. The functions in this set are of the form cosine n pi over px, where n is some natural number, 0, 1, 2, 3, and so on. In order to show this, we have to calculate the inner product of two elements of the set. Okay, now in order to calculate this integral, we use this trig identity, which states that for any a and b in real numbers, cosine ax times cosine bx is equal to the 1/2 cosine a plus bx plus cosine a minus bx. Applying this trig identity to our integral here, we have this. Now we have an integral in two cosine terms, which we can calculate directly. Okay. Now, when evaluating this in terms of the fundamental theorem of calculus, right, we have to plug in p and negative p to these sine terms. We see that when we plug in a p for x here, the p's cancel out, giving us sine of some integer, right, some natural number times pi, which is always equal to 0. So we can see that this entire sum is equal to 0. So what we've proven here is that any two elements of this set are orthogonal on this interval, right? And so for n equals, say, 0, 1, 2, on to infinity, we have an infinite set of cosine functions which are orthogonal.